give you 5 minutes.
Okay, is this on? All right. I'm really excited to be here today and share with you the latest results just published last week in the Astrophysical Journal Letters with this talented and diverse set of co-authors, many of whom are here at the meeting, and one of whom is the chair, so I'm sure I'm going to get a little extra time. Okay, let's get right into it. We've heard earlier in the week already about weakened magnetic braking, so I'm going to go through this relatively quickly. But basically, stars spin down over time as they lose angular momentum to their magnetized stellar winds. And if you simulate the Kepler field and what distribution of rotation periods you would expect to see as a function of effective temperature, this is what you would predict. And what you actually observe is this. And so the blue points obviously don't go to the long periods that are expected for old solar type stars spinning down in a Skumanich-like manner. And the question is that because of a detection bias, perhaps? We just can't reconstruct or detect those long rotation periods? Or is it weakened magnetic braking, which is to say a hypothesis that somewhere around the middle of main sequence lifetimes, stars actually stop spinning down? And if that were the case, then what you would expect is along this edge, stars with a variety of ages would pile up and hang out there for the second half of their main sequence lifetimes. So this was put forward by Jennifer Van Saters originally in a Nature paper in 2016, and then extended to this full sample of tens of thousands of stars in the Kepler field in 2019. So we can now answer these questions based on the results in 2 recent publications, I think both of which you've seen. So the answer to the first question, is it just a detection bias? We can't detect those longer rotation periods. The answer to that question is no. Oliver Hall showed that if you use a completely different method, astroseismology, to measure the rotation periods of these stars, that has completely different detection biases. And in fact, it's easier to detect rotation in astroseismic targets that are low magnetic activity. The distribution actually looks similar to the weakened magnetic braking model and supports that model with a very high degree of certainty. And the other question, do the stars with a range of ages pile up along that edge? The answer was provided very recently by Trevor David and collaborators, where once you get precise effective temperatures, so you don't smear out the diagram that we saw in the previous slide, once you get those precise effective temperatures, you can actually see the pileup along that edge, so a higher density of stars along that cutoff with a variety of ages from isochrones. So I'm going to proceed now under the assumption that you are all convinced that weakened magnetic braking is a thing that's not going to go away, okay? And let's try to understand, now that we know that weakened magnetic braking has consequences in tens of thousands of stars, let's examine very specific evolutionary sequences of stars and try to understand what causes it. Now, first I should tell you why you should be interested in this question in the first place. If you're interested in cool stars, then I think, like me, you'd be inherently interested in this because this new picture represents the most substantial revision to magnetic stellar evolution in a generation. And I'm trying not to be hyperbolic about it, but I really do believe that's true. If you're interested in the sun, then the sun actually appears to be beyond this magnetic transition already. And so it could be that one of the reasons we're having trouble extending our knowledge of the solar dynamo to other stars is because the sun may be a special case of dynamo theory that's occurring after this transition. And finally, if you're interested in planets, then it may be just a coincidence, but it just so happens that the only inhabited planet that we currently know about, life emerged from the oceans onto land around the time that this G-type host star passed this transition. as I'll show in the results to come. Now, in addition to telling you why you should be interested, I'd like to tell you, try to connect this to something that you already know and accept, okay? It turns out that Durney and Latour in 1978 put forward this idea that to sustain a magnetic dynamo, the Rossby number just can't be too big. This is when I was in kindergarten, so I relied on an older co-author to inform me about this paper. Now, there's two ways that you can get there, and they were motivated by the existence of the Kraft brake, which was discovered just about 10 years earlier. And that's the limit where the convective turnover time becomes too short. And the convective turnover time depends very, very strongly on stellar mass. And so you get a very sharp break in the HR diagram, above which convection zones are too thin to sustain a magnetic dynamo, and stars don't spin down. They stay rapidly rotating throughout their lives. But below that mass, they do spin down. The other limit is just when the rotation period becomes too long. And that is the weakened magnetic braking limit. So unlike the Kraft brake, the change in the rotation period happens on stellar evolutionary timescales or magnetic braking timescales. And so the deviation between a standard model and a weakened magnetic braking model accumulates on longer timescales. And so it's not a sharp thing. It's something that you notice more and more as a star evolves over the second half of its main sequence lifetime. And in fact, this shows the fractional difference in the predicted rotation periods in an HR diagram. And the biggest differences that you'd actually expect are on the subgiant branch after it's had the full second half of its main sequence lifetime to accumulate. Okay. So if you believe in the Kraft brake, you should also believe in weakened magnetic braking. It's just the other limit of the same concept. Okay, so the other thing that makes us believe that this may be connected to differences or changes in the stellar dynamo is that we see a signature of this effect also in stellar activity cycles observed by the Mount Wilson survey. And the template for this evolutionary change is 18 SCO. Well, so a younger star, HD 76151. Sorry, I should back up and explain this whole diagram. This is a diagram originally published by Erika Bohm-Vitens. It's rotation period versus cycle period. And you find that most stars fall along these two sequences, one of which may not exist. It depends on who you ask. But the bottom one is the one that we're concerned with. We think that's where the solar cycle came from. And basically, young active stars will, as their rotation slows, they move along the sequence and their cycles gradually get longer until they hit this critical Rossby number where weak magnetic braking turns off. And then the rotation period stays basically constant. And if we look at this evolutionary sequence of 18 SCO, a bit younger than the sun, Alpha Centauri, a bit older than the sun, and 16 Sig, which have constant activities, still has magnetic activity you can measure, but no cycles, then what we see is that cycles apparently grow longer and weaker over time during the second half of main sequence lifetimes. And we see the same general pattern in both hotter and cooler stars. So the prediction that we actually put forward 5 and 6 years ago in the original papers in 2016 and 2017 is that one way that you can do this, create weakened magnetic braking, is to just concentrate the field, the magnetic field, into smaller spatial scales, because it's the larger scales that produce most of the braking. So in the second half of this talk, I'm going to show you these evolutionary sequences for the hot stars and for the solar analogs, results from spectropolarimetry, where we'll actually measure the geometry of the magnetic field for those stars to the extent that we can. But let me just take a step back and give you the basic picture that we put forward in 2018, and it's basically right as far as we can tell from everything that we've learned since then. And that is, so why does this happen? We think that in the limit of slow rotation, rotation becomes mostly uniform. That the loss of shear disrupts something like an alpha omega dynamo. And so you no longer have the omega effect to convert the field from poloidal to toroidal. And then the disruption of that dynamo leads to the collapse of the largest scale field. So, and the dipole field has the largest Alfvén radius, which is the lever arm that is responsible for the loss of angular momentum. And so if you just move more of the field from larger to smaller spatial scales, you shut down magnetic braking effectively. All right, so in 2019, and again, in just last year, we went to the Large Binocular Telescope to try to test these ideas to measure the large-scale magnetic fields of evolutionary sequences of stars. And I would really like to thank the telescope allocation committees for allowing us to use one of the largest telescopes in the world to observe stars that you can see with your naked eye. That's and for which we may only get non-detections that are statistically significant, right? It's a tough sell, but thank you. I think you'll agree that it was worth it. So the first evolutionary sequence for the hot stars, we have 88 Leo, which is down there on one of the sequences, normal cycle, hasn't hit the critical Rossby number yet. We get a clear detection in the Stokes V circular polarization. Just to emphasize, the full scale here is plus or minus 1 part in 10,000 polarization. And for Rho Core Bohr, which is a significantly older star, constant activity, so not cycling, we get a statistical non-detection, and we can use that non-detection to set upper limits on if you assume axisymmetric dipole or quadrupole or octupole. And in combination with additional constraints from X-ray fluxes, rotation periods, global properties like mass and radius, you can pump those into Adam Finley's predictions of angular momentum loss. And what we find, those are shown in green, we find that between the ages of these two stars, across the transition, the wind braking torque decreases by more than an order of magnitude. Now, we only have these snapshot observations, and so it would be really nice to actually know the full magnetic map of the stars to make this more secure, to remove those ambiguities of the snapshots. And that's what we ended up doing for the solar analogs. So these are full magnetic maps from the BQUL collaboration for the two youngest stars in our evolutionary sequence of solar analogs. So again, at 2.6 gigayear, a young solar type star with a normal cycle, and 18 SCO, just a bit more than a gigayear later, just above that lower activity sequence. And again, we find more than an order of magnitude decrease in the magnetic braking torque during this 1 gigayear interval. And for context, the theoretical expectation between the ages of these two stars is that you might decrease the magnetic braking torque by a factor of 2, and an additional factor of 2 by the age of 16 sig. Okay, during this stage, that change in wind braking torque is dominated by both a factor of 3 from mass loss rate changes in the mass loss rate, and another factor of 3 by the changes in the strength and morphology of the magnetic field. So we can attribute which physical mechanisms are actually responsible for this change. Now, extending this to the old solar analog, 16 sig A and B, where again, we get from LBT data, these statistical non-detections, and we use it to set upper limits, assuming different geometries. We continue to use the torque that we measured from the full ZDI map of 18 SCO, but we observed 18 SCO again as a control for the positive detection of magnetic field. We didn't not detect it in 16 sig because we couldn't detect it. We didn't detect it because it's not there. And so there's a modest continued decrease between 3.7 gigayear and 7 gigayear, another 20% or so, despite the fact that the stars are expanding significantly during that period of time as well. So it's counteracting the tendency to stay at the same rotation period. Okay, with that, I will put up my summary of conclusions and take your questions. Thank you.
Please. Okay, just, yeah, 1 meter below. Thanks.
Travis, This is Peter Williams. Actually, I track satellites for a living now. You can ask me how if you want, but just curious observer. So the what physically explains the slow secular change in field flipping? I mean, if braking is basically turned off, what's changing?
Do you mean in the small change in rotation period as it's ascending, getting a longer cycle? Or
yeah, is that it? Just a small change in rotation period is enough to?
Yeah, and it's basically physical expansion during the second half of the main sequence life. So it still conserves angular momentum. As it bloats a little bit, it'll slow down just because of the change in the moment of inertia.
Okay, thanks.
Steve Saar. Let me just note that 166620 that's up there has recently by Baum and by Lund et al. Been noted to be a, yes, you got it, going into what looked like a Maunder minimum. It might be the first clear Maunder minimum star, and that might also support the idea because it's starting to hiccup just like the sun.
Exactly. And this critical Rossby number can also be translated into a critical activity level. And the idea, I think, is that as stars cross this activity level, as their activity levels growing lower over stellar evolutionary timescales, the cycles might become intermittent until eventually they evolve entirely below that level, that critical level, and then they'll just stop cycling entirely. For this star, that critical activity level corresponds to roughly the mean activity level during the time that it was cycling. So it was spending half of its time below this critical Rossby number or below the critical activity level. And so it might explain, for the sun, it's also near the minimum level that we currently have, a little bit above that. And so as stars spend some of their time below this level, they might develop this intermittency to experience grand minima. And it's like a sputtering as the cycles are beginning to disappear.
Hello, Travis. This is Julian from the IP. I'm going to throw you a hard question here. Can you go back to your ZDI maps for your the ones that you have, the comparison, that one? How is it that you're reaching plus minus 90 degrees in latitude with Zeeman Doppler imaging?
Oh, well, I presume that these are plots by Borosaikia, but based on the original data from Petit in 2008. And there is a portion of this that is not visible in both cases. So that's an artistic license, I would say.
Okay.
Yeah, no, you don't, of course.
Yeah. Unless they're edge on, and then you probably not see anything.
Do we have a microphone here, please?
Yeah, thanks. Nice talk, Jean-François Donati from Toulouse. I wondered how much of this can be extrapolated to M dwarfs, because as you've, my question is because we've got a lot of data for Rossby number larger than 1 stars in this regime of mass. So I wondered whether all this can be applied, in particular the smaller, the weaker braking.
Yeah. So the good news for the M dwarf community is that from the standpoint of Rossby number, M dwarfs are all young. All of them are in their infancy. And so even the oldest white dwarfs or M dwarfs that are the age of the universe have not reached this critical Rossby number and are unlikely to do so in our lifetimes, I'd say. So you're safe to develop gyrochronology relations among the M dwarfs because they won't experience this disruption, although they may experience other disruptions that we've heard about this week.
Yeah, sure. All right, we have to quit here. Whenever it's getting interesting, of course, we have to quit. So let's thank the speaker again. Thanks, Travis.